Okay, yeah, I think we can get started here. Thank you guys for being here again. It's great to have some community to share this stuff with. See, this is the third episode now. Third week we've been looking at BigBird. The first week gave some basic introduction into sparse attention, and then last week we looked at applying transformers to a multi-GPU environment and seeing how you do that. So this week I've got, I think this is the last week probably that I'll focus on the architecture of BigBird. I think I've kind of explored everything here that I was hoping to understand. So I can share what I've learned with you guys. To start off, let's get back into the right mindset here of what BigBird is all about. So BigBird is for applying BERT to longer sequences of text. And the way it does that is basically by making BERT more memory efficient and computationally efficient so that it's practical to run on longer sequences. And the way it does that is with this technique called sparse attention. And what that means essentially is that instead of each word in the sequence attending to every other word in the sequence, the words only attend to some words and not every word. And specifically, each word in the sequence attends to its neighbors, the tokens around it, some randomly selected tokens, uniformly random, and some global tokens. And these attention connections are illustrated with these adjacency matrices, like this one. So I kind of interpret these. I don't know if the authors interpret them the other way around or not, but I've been interpreting it as like each row represents a input token or query, and then the columns represent the context or the key vectors. So if you go from Jacob to that means like Jacob is the input word and we're attending to the. So yeah, and then these are the kind of these salmon colored ones are the randomly selected tokens, the blue are the neighbors, and then these GATs, global attention tokens, every token in the sequence attends to those, and then they also attend to themselves and to every token in the sequence. So they're fully connected, just like the original attention implementation. All right. So that's the review. So what they implement for BigBird, they actually call it Block Sparse Attention. And what that means is that when they show these adjacency matrices, each of these squares actually represents a block of tokens. And the default block size is 64 tokens. So if you're looking at, let's take this block as an example. So this means that these 64 tokens in the sequence are attending to these 64. So the scale of this is a lot larger than our kind of trivial example here with like 10 words in it. So the actual size of this matrix depends entirely on the length of your sequence. So this is just an example. So this is, there's 12 of these blocks here. So if the block size is 64, then this is actually 768 tokens. So that's the length of this example sequence. And yeah, the neighbor, attending to the neighbors, it's not just one word to either side. It's actually 192 tokens. It's one block to either side, plus plus its own block. So these 64 tokens all attend to these 192. So much wider range there. And then finally the global tokens. So there's 2 blocks worth of global tokens by default, and so that means there's actually 128 global tokens. Right. And the whole point of this this blocking mechanic is that it improves it makes better use of the GPU, more efficient GPU use. And Hugging Face made a blog post where they kind of explain how block sparse attention is implemented. And they had this insight in there that I thought was really helpful. So they said one of the major contributions of BigBird is the proposition of a block sparse attention mechanism that allows computing sliding, global, and random attention effectively. Let's see. Yeah, so longformer and BigBird are actually very similar. We kind of talked, I think, last week about, like what's the difference really? What did BigBird introduce? Because longformer uses sparse attention as well. And apparently, I haven't read the longformer paper, so I'd be curious to get a better handle on this. But it sounds like what they're saying here is that this block technique is unique to BigBird. And yeah, so a lot of there's a good chunk of the appendix that's devoted to explaining how they implement block sparse attention efficiently, and that's kind of what this Hugging Face post is about as well. So it's kind of it's more about like clever GPU tricks. So I didn't dive into it quite as deeply, but basically, let's see. Yeah, so when you look at one of these adjacency matrices, what it's saying is that, so for this block, what needs to happen is that the query vectors for these 64 input tokens need to be multiplied against these 64 key vectors for these tokens. So there's a matrix multiplication that happens here. But then we've got a bunch of those, right? And they're spread out over the matrix. So they're potentially sparse, which is bad because GPUs don't do sparse matrix multiplication efficiently. So there's a couple things. So that with the global tokens, those you can do efficiently because they are dense, right? So this is saying that we need to take the 768 query tokens and multiply them against all 128 global tokens. So that's a nice big dense matrix multiplication. And then I think where the trick comes in, where they got clever, is with this sliding window attention. And again, I didn't fully dig into that to make sense of it, but somehow they're able to implement these matrix multiplications for all these blue blocks. They can do that pretty efficiently. And then finally, the random tokens, the orangish blocks, my understanding is that those are not efficient. That there's an operation called a gather, which I'm not familiar with, but from the name and from how it's used, I think what it means is that they essentially have to do a selection. They've got to move some stuff around in memory. They've got to pull together these different blocks in order to combine it all into a single matrix multiplication. And that's not as efficient. Yeah, okay. So I wanted to cover the block stuff because I think it's valuable to kind of have that have the right scale in mind, because we for explaining this stuff we use these like small sequences, but really once you put the blocks in, it's like we're talking about a window of 192 tokens, not just 3. So I think it's good to have that perspective. But I wanted to cover kind of why, how is sparse attention able to work given that we've just dropped a bunch of attention, and also, let's see. I feel like there's a second piece to that, but that's okay. I'll just go through this. So we've lost. It's great that we've cut down on compute, but we've lost some useful connections. We So maybe a good example here is, it seems like the word Jacob should attend to the word firm. It probably needs to know a little bit about firm since Jacob works for the firm, but we've dropped the attention there. Jacob is not attending to firm. So there's still a way, though, for the Jacob token to learn some information from the firm token. And the way it does that is essentially through multiple layers of the model. So we've got, so Jacob doesn't attend to firm, but the word sent attends to firm. So the token for sent gets to pick up some information from firm in one layer. And then in the next layer, Jacob does attend to sent. So Jacob gets to learn some information about firm from the sent token. So there's kind of a hop there. And then the global tokens also provide that as well, right? So Jacob attends to the global tokens, and the global tokens attend to sent. So that's another way, I'm sorry, to firm. So that's another way for Jacob to learn about firm. But yeah, it means that so however many hops it takes to get to the word, that's how many layers there needs to be for the information to travel. So in this case, it takes 2 layers for information about firm to reach the token for Jacob. So so understanding that, I think, kind of explains the rationale for how they chose what to attend to. So my understanding is that they do this, they attend to the neighboring tokens because these tend to be important. It's likely that you want to attend to tokens in the vicinity of the word that you're looking at. And then the random tokens and the global tokens provide this function of creating paths to all the other tokens. So so the global tokens are maybe oversaturated since they attend to everything, but they are a short path between any 2 tokens. And then the random tokens are an additional path that are less saturated, and the authors kind of draw on graph theory to, I believe, explain that when you make random connections like this, it kind of guarantees that it'll generate a graph that has a relatively short distance between any given pair of nodes. So I believe that's the rationale there and why they pull in the graph theory. All right, so last couple things here. There's this notion of ITC versus ETC, and then I'll talk about some specifics of the Hugging Face implementation of BigBird and of sparse attention. So ITC and ETC stand for internal transformer construction and external. And ETC is the version of the model that actually uses these made up global attention tokens. So these are only in ETC and not in ITC. And something interesting to note about that is because we're adding these global tokens, we're making the sequence longer, right? However many words we had in our sequence originally, we're now adding, what was it, like 128 extra tokens to the sequence, and that increases the amount of compute that we have to do. So that's kind of like a disadvantage of ETC. But it doesn't require any random blocks necessarily. You could do random blocks, but when the authors used the ETC version of their BigBird model, they applied it to question answering benchmarks. They did not use any random connections. They just relied on the global tokens to provide that connectivity. So I think that's a pro, because as I understand it, that random attention is not as compute efficient as the other kinds, as the sliding window and the global tokens. So another trade-off there. And then ITC, the way they replace the global tokens is that they actually, instead of like creating some imaginary global tokens and adding those on, they choose some of the existing actual tokens, the real tokens, and they make those globally connected. So they have those attend to every other token in the sequence. And I've got a good example of that in the next section here. And if you look at their benchmark results, ITC is what they used for long document classification tasks. And I think they had some rationale in there for why they chose to use ETC for question answering and ITC for long document. There's something about the wider context being more important for question answering, I think. I'd have to go look at that again to say that more correctly or confidently. Something like that, though. So the Hugging Face implementation is specific. It's got some hard-coded design choices in it. So I think it's interesting to look at since it's what we're actually using in our example code. So Hugging Face is currently just ITC. They don't support ETC. And there's a few things that are hard-coded for you. The sliding window size is 3 blocks. Just like we've seen in these illustrations, but you can't change that. And the number of random connections is 2 blocks, and you can't change that either. So because it's ITC, there's no added global tokens. Right, yeah, their blog post explained, I was really curious about this, so I wanted to know, all right, so if you're doing ITC and you're picking some existing tokens to use to make them globally connected, which tokens do you pick? And so they explained in their blog post that they pick the first 64 tokens, attend to all of the others, and then the last 64 tokens are also made global and attend to all. And then these columns here kind of show that all of the tokens are attending to the first 64, and all of the tokens are attending to the last 64. So it creates this kind of square of global attention. Anything else to say about that? I've got a couple more miscellaneous details here. Yeah, I thought it was helpful to understand that sparse attention does not affect the number of parameters in the BERT model. The query, key, and value projection matrices are still dense. They're still the same as they were in BERT. And sparse attention really is all about when you actually execute the model, it just changes how you compute attention. Yeah, so it affects the specific calculations done, and in turn it affects the amount of memory required for the intermediate results. Yeah, and so another kind of interesting implication of that is that you don't actually you can turn off sparse attention, and there's the Hugging Face implementation supports that. There's a parameter for that. So, and I think that's interesting because BigBird was pre-trained with 4,096 positional encoding vectors compared to BERT's 512. So BigBird's hard limit on sequence length is a lot higher. And they also say that the authors also say that sparse attention really only makes sense if your sequence length is greater than 1024. So if your length is somewhere, more than 512 but less than 1024, then You can't use BERT necessarily because it doesn't have enough of these PE vectors. But you could, if you wanted, use the BigBird, the pre-trained BigBird, with full attention, and hopefully that would do better. Yeah, all right. Let's see, how did I do on time there? Felt a little longer. Yeah, it's good though. So what I'm working on now, I've been working on a Colab notebook to illustrate how to apply transformers to a multi-GPU system. That's what we looked at last week. I did figure out the last week when I showed you guys that I had run it on 8 V100s, and it was actually slower than when I ran on a single GPU. I learned this past week that an important rule of thumb is that you want to increase the training batch size linearly with the number of GPUs. So if you're doing a batch size of 32 on one GPU, then for 8 GPUs, you should have a batch size of 256. And that's how you'll actually keep all those GPUs busy and benefit from the parallelism. So once I did that, I got a good speed up from the multi-GPU setup. And then, yeah, yesterday I was working on that notebook, and Lambda Labs was completely at capacity. They didn't have any GPU instances available. So I've switched to Amazon SageMaker, which I guess, I don't know if switch is the right word. Yesterday I used SageMaker. It's another option. It's part of AWS, so I really liked the simplicity at Lambda Labs. SageMaker feels more like an AWS product with like tons of configurability and this rich ecosystem with lots of options. So it's a little more overwhelming, but it provides pretty much the same functionality. You get a multi-GPU instance that is all set up for you to run machine learning experiments using Jupyter notebooks. It's twice the cost of Lambda Labs, so Lambda's marketing was accurate there. You can get an 8 V100 server at Lambda for $12.50 an hour, or a 4 V100 server at Amazon for like $12.25 an hour. So it really is like twice the cost. And so once that's done, I'm kind of wrapping that up. I'll add that to the BERT collection, and then I'll be working on a basic example of applying BigBird to long document classification. And that'll let us see kind of what it's like in practice to work with it. And hopefully we'll see some sometimes it's hard to get improved results out of these BERT variants. I feel like I feel like BERT out of the box does really well, and some of these variants, it's like if you want to get a good benchmark score, you've got to tailor it more or something. More hyperparameter tuning is required or something like that. So it'd be sweet if BigBird just kind of like delivered. That would be nice. We'll see. So we can move on to some discussion here. One kind of question I have, maybe for myself, if anyone wants to weigh in on it, great. Something I realized about using multiple GPUs for BigBird is that, I've been thinking of it in terms of these long sequences do require a lot of memory. And even with BigBird's simplifications, you can still run out of memory pretty quick on just a single GPU. So more GPUs means more memory. However, I think that's only true if I employ model parallelism instead of data parallelism, which means dividing the model across the GPUs instead of replicating the model and having each GPU work on a different chunk of the data set. So it seems like the point of data parallels is really just to get you through your training set quicker. But if your goal is to have more memory for your model, then model parallelism seems like what I need to do. So might have to look at that. All right, so I will stop there and we can kind of open it up for some discussion. I'm going to pull up I forgot to pull up the discussion doc earlier. Let's see, what did I call that? Weekly, it's like Q&A. Yes, there we go. Bring that over. Oops. All right, I'll have to add this to my, I have a little checklist of stuff that I do to get ready for this. And this wasn't on there. So I have to make an addition. Cool. Yeah, so any questions, guys? Anything about, I guess, BigBird first would be great. And then if there's nothing more that we want to talk about with BigBird today, then we can just open it up and talk about whatever. Keep setting this up.
I had one or two, if I can jump the line here a little.
Yeah, go for it.
So did you get a sense of when the random tokens in the adjacency matrix are applied, how is that sort of applied on a very low level? Is it like each run through the model, a different set of random tokens are assigned, or is it like one through, what are the kind of details there?
Yeah, I had that question too. So it's kind of like, does the pattern of random attention change with each forward pass, or is it somehow hard coded? I wonder.
I think Jay's raised his hand.
Yeah. Go ahead, Jay. So we can mute.
Oh, there you go.
Some audio trouble.
Maybe. Yeah.
I'm thinking maybe it has to be on every forward pass because you don't know the size of the input until runtime, right? So it's like you've got to pick two random blocks out of what's there. And what's there can change on every execution of the model because it can accept variable length sequences. So in order, so one input might be length 768, and then the next might be 2048. So include two blocks of random tokens in both cases. Seems like the random pattern would have to be generated on the fly. Yeah, regenerated for each. So there's my conjecture. But yeah, that's a good question. Another one I had kind of, I don't know, that's not related, but it's like how do they initialize those global tokens? Maybe less interesting since the Hugging Face implementation doesn't actually use the global tokens. But something that I didn't see mentioned anywhere. Cool. Let's see. Yeah, did you have anything else, Nick? You're muted.
Now it's my turn. Yeah, no, Jay's audio is not working. But he asked, can you give an example of global token? So I think, yeah, as Chris was saying, it's for the ETC model, they add global tokens, and for the ITC, and in the ETC, I think it's in sort of the same vein as BERT has like a CLS token that's sort of added to the front that it's not specifically about any one word. It's just sort of there to take some of the information processing load and route things through it. And for ITC, Chris, you were saying they just pick the first and last token?
First and last block. Yeah.
Okay, first and last block.
So it's, first 64 tokens and last 64 tokens. With the block size is configurable. That is something you can change, but the default is 64.
Okay.
Yeah, I like that analogy. It's like the GATs are similar to the BERT's special tokens like CLS. Yeah, they're made up and exist for what would you say there? It's like they're there for BigBird to use.
Yeah, to like share some of the information processing load, I guess.
Yeah.
I guess in BERT, CLS is the very specific function of kind of serving as a whole sentence shorthand for the whole sentence vector.
And it becomes that because of the final model objective, right? They use that CLS token to do like predictions. So BERT is motivated to encode that information into the CLS token.
Yeah.
Does that help, Jay? Or is there another aspect to your question there? And you're right about the purpose. Yeah, it's to give it global context, to give it access to information from the entire sequence.
Oh, the CLS token is just in BERT and a lot of sort of BERT variants. It's so the input might be one or two sentences. And in front of all of those, the very first token, sort of artificially inserted, is it's just a CLS token, and CLS supposedly means classifier, but it's just a token that has no real meaning. It's just one of the vocabulary items, and they sort of route a lot of information processing through this CLS token, and the end goal is that it serves as some kind of, given the route, or given the objectives of BERT, it just is supposed to serve as some kind of shorthand for the whole sentence. So it's like each word in the sentence has its own vector, but the CLS token is supposed to be a kind of like simplified version of everything that comes after it. It's just used for things like, classification and, as a shorthand for the vector.
Nice. Thanks, Nick.
Yeah, it's kind of hard to say. I remember reading quite a few things, and the authors are very cagey about calling it a sentence vector. And they're saying, no, don't interpret it like that. It's not necessarily a sentence vector.
Yeah.
Like they were very rigid about this is an information processing token at the front that has these properties. But they were really hesitant to call this your sentence vector or anything like that. Yeah.
I think that's because of the pre-training tasks, right? Like if you're doing next sentence prediction, then it's like if you were doing if they had pre-trained it on document classification, then the CLS token might be a pretty good sentence embedding. But they trained it on next sentence prediction. So the CLS token somehow encodes like, does sentence B come after sentence A? It encodes whatever information they need to make that decision. So that's not necessarily a good representation. So it's like if you tried to use the CLS token out of the box without doing any fine tuning of BERT, then I could see why it wouldn't be ideal.
Yeah.
But it is good if you fine tune BERT properly, then it does seem like CLS is a good sentence embedding potentially. Any context specific to the application.
I mean, I'm not sure about for your specific domain, but you can discard the CLS token. You don't necessarily need it. Whatever transformer architecture you would go with probably wouldn't include if you're doing time series data, you probably wouldn't want next sentence prediction as part of the thing that was used to pre-train the model. Is that true? That's sort of my hunch, but in any case, you don't need the CLS token. It's helpful for pre-training and sort of, I think it makes the model better in a lot of ways, but at runtime or execution time, you can discard it. You don't need it.
All right. It's always there on the input because BERT expects the input to be formatted a specific way. But yeah, you don't have to on the output of the model. You don't have to do anything with it. Right. Yeah, and then the global tokens don't. Right. I don't think there's anything application specific about them. I think they're more about helping tokens reach or receive information about other tokens that are farther away in the sequence, even though they're not directly attending. Cool. Any other BigBird questions? And if not, since it seems like not.
I got one more.
Yeah.
You said that the BigBird has the same number of parameters as BERT.
Yeah.
How does that work, or how is that justified?
Okay, well, so first of all, I don't 100% know that that's true because maybe there's like some subtle difference in there that I'm not capturing. But
yeah.
I think my point there more is like I was trying to wrap my head around like what does sparse attention mean for the model, and like where is it implemented? And yeah, I realized it's like it's not. Let's see. What is there any illustrations that would help for this? So, the adjacency matrix represents which attention calculations to perform. But the first step is to take all of the tokens in the sequence and multiply their embeddings against the query matrix, the key matrix, and the value matrix, right? So you get these projections. For each token, you get three different vectors: a query, a key, and a value. So that step happens first before any attention calculations are done, and that happens whether you're doing sparse attention or not. And in terms of the model's parameters, it's those projection matrices that are the actual parameters of the model, the K, Q, and V matrices. So there's nothing about sparse attention that impacts those projection matrices. You still need them. They're still dense. Yeah. Did that clarify it at all?
Well, yeah, I see that the query key, like those are still dense projections. But yeah, so where is the sparsity of parameters? Where does that exist?
Right. Yeah, that's a good way to put it. So I think it's not sparsity of parameters. It's sparsity of calculations, and therefore of also of attention scores. And I think it's the attention scores that take up a ton of GPU memory.
Is this something like a lot of the values are set to 0? Because that's the definition of sparsity here, so that, the matrices are still as big as usual, but a lot of them are set to 0. So the calculation is faster or null, or I don't.
Right. It can't be that, because that would still use just as much memory.
Yeah, you would still have to calculate it.
Yeah. So I think, let's see, maybe we could try to guess at this a little bit here. So if you were to do, so full attention for this example means 12 inputs times 12 context equals 144 attention scores. If instead we've got each token attending to, let's say, 6 tokens, then it's 12 inputs times 6 context equals 72 attention scores. So if you were to gather, so part of the magic is in how they take all these vectors and mash them together so that it becomes a dense matrix multiplication again. But I think the upshot is that you've got less, you're doing fewer dot products in the end. And because they mash them together, it is a dense calculation, not a sparse one. So let's see if I can. There's both the.
That helps. Yeah.
Yeah. paper's so long. I hope I can find what I'm looking for. They've got, yeah, so it's like you can read through this if you're interested. They try to illustrate how like you take these different blocks and then squish them together, into one tensor. I don't know if that does anything to clarify it. But yeah, it's this like grabbing the different blocks of vectors, combining them together, and then makes it a dense matrix multiplication again.
Okay. That helps, that after sort of the gathering stage, it's then a denser computation.
Right.
A dense computation, but it just has fewer attention scores.
Yeah.
Okay.
Yeah, that was a good question. I wish,
at least conceptually I'm there. I'll probably look at that section to see what their little Tetris game means.
Yeah. Yeah, I think it's really if I understand right, it's the like they've got a clever trick for implementing this like these blue calculations. The word rolling is in there. But yeah, it's like otherwise it's like you've got these vectors stored in memory, and you're accessing different parts of the matrix and trying to pull them all together. So that's got to be inefficient, or creates overhead. How could I summarize your question there? Because that was a good one. That'd be a good thing to incorporate in here. It's like I like the question of like are the parameters or BigBird's model parameters sparse in some way? It's kind of part of it. But no. KQ. I always get that backwards. QKV. And then the sparsity is in the number of attention scores calculated and stored, I think, is the key bit, maybe. Right, because QKV are like, they are like Q is 768 by 768. Full attention for 4096 by 4096 is a lot bigger. So this is the piece that they're making sparse. Cool. So Jay, has there been non-NLP applications of BERT? I guess I should ask any other BERT questions before we move on. Those are some good ones. I like that. I'm glad get to add those. I think those will be some good clarifications for the tutorial. I like that. But yeah, all right. So let's go on to whatever you guys want to talk about. Have there been? Yeah, it's 7. We got like 10 minutes. Great. Have there been non-NLP applications of BERT, like in image recognition or econometrics or social science, for systems modeling tasks? Systems modeling, interesting. That is a space I know nothing about. Systems modeling. We did talk a little bit last week about applying, or it's like you can try applying the transformer architecture to any problem which is a sequence in nature. So genomics is kind of the cool example that's in the BigBird paper. Do you have any insight, Nick?
Yeah, I think it's been used a lot, but it's more specifically transformers architecture. I think BERT is pretty, it uses the transformer architecture for text classification. But if you look up, transformer architecture for image classification, you'll get a lot of results because people sort of take the core architecture and translate it into all these other places. So yeah, I think you're interested in time series. You might try just have a look around at transformer architectures applied to time series. It might be a little, might be a little more thrown if you're asking for time series BERT. But yeah, I think I don't know much about it, but I know it exists out there that people use the transformer architecture for different modes of data and different fields. So.
Man, why image so they've tried the transformer architecture in place of a convolutional neural network? Is that the idea?
Yeah.
Wow.
I have no idea what the details of that architecture look like, but yeah, I've seen that applied in quite a few places.
Yeah.
Okay, yeah, thank you.
Nice.
Vision transformers.
Right, and the difference between BERT and the transformer is that kind of is it that the key innovations in BERT are really just like the pre-training tasks that were used to train BERT on huge amounts of text. But really it's like they're just using the transformer architecture. And so BERT is just kind of like a text-specific use of the transformer. And also the original transformer had like both an encoder and a decoder, so it could do sequence-to-sequence tasks, whereas BERT is just the encoder side. But yeah. Right. So if you were interested in transformers for time series data, you want to avoid the key term BERT probably. Yeah, Vinay, do you know anything about why the transformer makes sense for vision applications? I think it's like the transformer is good for taking a sequence of things and encoding rich embeddings for each of those things in the sequence. So what's the sequence in the context of an image? Like image patches?
So actually the innovation that there is a paper called image is worth 16 by 16 word. So what they do is they convert the image into a sequence of 16 by 16 chunks. So they segment the whole image into 16 by 16 chunks, and that's the sequence. And that's what they feed into the transformer model.
Interesting. Do you have a sense for how well that approach does compared to, convolutional neural networks or something more sort of traditionally used for vision tasks?
I mean, there has been very few good research in terms of transformers for vision. There is a paper by Facebook called Data, and then this vision transformer is from Google. But there hasn't been much comparison in terms of, let's say, resonate-backed architectures, which are like pretty good for vision tasks, right? Yeah, I mean, there hasn't been much comparison, but seems like vision transformer is the new bird for vision tasks.
Oh, interesting. Yeah, we'll have to check that out.
And the paper from Facebook is called Data, DETR. DETR.
Yeah. Yeah. Cool.
I think Hugging Face also has released a VIT implementation, but it's still in our testing stage.
Oh, thanks. Yeah, I'll have to check this out. It's time I looked at attention mechanisms applied to other kinds of data. It's a good place to start.
Yeah. Yeah, it's interesting. They're still using a CNN to get some image features, but then then using it for more of a sequence-oriented task, something like that. Nice. Yeah, thank you. It's a really popular repository too.
Yeah. VIT doesn't have a CNN module within it. It's totally transformer based. So that's something different from Data.
Keyboard. Cool. Well, we've only got a couple minutes left, so I think I'll probably wrap it up there unless anyone has anything they're super itching to ask. I read some people talking universal network platform. Yeah. Cool. Right, so next week I think will be some kind of like hands-on with BigBird in terms of coding with it and trying to apply it to some examples. I'm going to start with the 20 newsgroups data set, which is this old kind of crappy data set, but it's got really long text in it, and from some past experiments I've done, the sequence length seems to matter. Like if you can handle more text, you can do better on that task. So I'm going to start there. If anyone's got a good document classification data set that they'd like to see BigBird applied to, I'd be super interested in that. It'd be great to have something else to try it on. But yeah, I'll share what I got next week. So thank you guys. It's been fun again, and I'll see you next week.
Bye.